Log on, tune in, find out. Another good idea from Cambridge.
The microphone seems to be working, yes, great. Okay, so what I want to talk about is joint work with, and work in progress, I guess, with Andrew Dancer and Andrew Swan. And so we've been trying to find an analogue in Hyperkahler geometry of a construction due to Gilliman and Jeffrey and Shamar about 10 years ago of symplectic implosion in symplectic geometry. So what I want to do is start off by telling you or reminding you a bit about symplectic implosion and then move to the Hyperkahler situation. So for symplectic implosion, so go over here maybe. So let's set up the ingredients. So I want to have X a symplectic manifold, so with a symplectic form omega, closed non-degenerate 2 form, and I want to have a Hamiltonian action of a compact and probably connected, so that's not going to be very important, group K. So Hamiltonian action meaning that it preserves the symplectic structure and that there is a moment map. So let's have mu or momentum map going from the symplectic manifold X to the dual of the Lie algebra of the group, and so it's defined. It has to have the property that, well, I want it to be K equivariant with respect to the given action on X and the coadjoint action on here, and I want its derivative in the direction of any element of the Lie algebra to be dual with respect to the duality given by the symplectic form to the one form, which is the derivative of to the vector field, which is the infinitesimal action of the element of the Lie algebra. So in this situation, then we can talk about symplectic reduction, which has been studied for many decades and is known to be related to geometric invariant theory and so on. So the symplectic reduction at some point in the dual of the Lie algebra is just the inverse image of this point under the moment map, quotiented by the stabilizer of the point zeta under the coadjoint action. So here this k zeta is the stabilizer of zeta under the coadjoint action. Okay, and so it turns out that this is has a natural induced symplectic structure, and it'll be a symplectic manifold, or if it's smooth, or at least an orbifold if zeta is a regular value of the moment map. So, and in particular, I guess when zeta equals 0, then we're looking at the symplectic quotient, which links up with geometric invariant theory if you're in an algebrogeometric situation. Okay, so that's symplectic reduction, but then what I want to tell you about is symplectic implosion. And so symplectic reduction, in a sense, gets rid of all the k-action quotients by the k-action. Symplectic implosion just gets you down from the full K action to the maximal torus. So in some sense abelianizes things. So for symplectic implosion, let's fix a maximal torus of K, and with Lie algebra sitting inside the Lie algebra of K. And of course we have the Weil group W, the normalizer of T over T, of course acting, and these decompose into Weil chambers. And so let's look at fix a positive Weil chamber in the Lie algebra, in the dual of the Lie algebra of the maximal torus. And so, of course, we can identify this with both the quotient of the dual of the Lie algebra of the torus by the Weil group, and with the co-adjoint orbits in the dual of the Lie algebra of the whole group. So in this situation, then, what symplectic implosion, the description of symplectic implosion. So, as I said, this is due to Victor Guillermin, Lisa Jeffrey, Rej Ma, and I think it was published 10 years ago. So in this situation, what they look at is what they call the imploded cross-section of X. And this is something which, like the symplectic reduction, has an induced symplectic structure on it. It's usually singular, but has a stratified symplectic structure. And the way that you get it is you take the inverse image, not of a single point, but of the positive Weil chamber under the moment map. And then you do a bit of collapsing, so modulo some equivalence relation, where the collapsing that you do is just essentially on the boundary of the positive Weil chamber. And so we have that X gets identified with Y if and only if we have that X is K times Y for some K which lies in the commutator subgroup of the stabilizer of the common image of X and Y under the moment map. So this is with zeta equals mu of X and mu of Y. So if we look at a couple of examples, maybe I'll leave that up there for the moment. So I guess the simplest non-trivial example is when you take K equals SU2, and so then the positive Weil chamber is just half line, and so if you're in the interior of the positive Weil chamber, well, this always happens. The stabilizer is the torus, and so its commutator subgroup is trivial. So you're not doing any collapsing on the interior of the positive Weil chamber, but at 0, the only boundary point, then, well, then the stabilizer is just the SU2 itself and its own commutator subgroup. So in this case, we have that the imploded cross-section, the symplectic implosion, is given by the inverse image of 0 quotiented by SU2. So this is the reduction, and then we have the inverse image of the interior of the positive Weil chamber. So we're taking this and then we're compactifying, if you like, by adding in this this extra bit on the boundary of the positive Weil chamber. And we've got a similar picture for that's slightly more complicated or interesting, of course, for K equals SU2. So then we have the standard picture of the positive Weil chamber, and in the interior, as before, we have that the stabilizer is the maximal torus, the commutator subgroup is trivial, we're not doing any collapsing. If we're on the boundary but not at 0, then we have here that the stabilizer is SU2 cross U1, I guess, and the commutator subgroup that we're collapsing by is just SU2. And at the origin, as before, we're collapsing by the full group. So here we have okay, so we're taking the inverse image of the positive Weil chamber under the moment map, and then we're doing this collapsing by SU2 on the boundaries except at boundary points apart from 0 where we're collapsing via SU3. Okay, and so the so as I said, this imploded cross-section, and it's given the quotient topology that you'll get from the equivalence relation, but it inherits a symplectic structure from the symplectic structure in X, and it also inherits an action of the maximal torus, which is Hamiltonian, so it preserves this symplectic structure and has a moment map, and the moment map going from the implosion to the dual of the Lie algebra, well, it's just the composition of the natural map that you'll get from here to here, composed with the inclusion of the positive Weil chamber. So it's easy to see that the moment map going from inverse image of the positive Weil chamber to here behaves nicely with respect to this equivalence relation, so we get an induced moment map like this. And then it also has the property that if you take a point in the positive Weyl chamber and you look at the symplectic reduction at this point, then, well, you've got two symplectic reductions you can look at. You can look at the symplectic reduction of the original symplectic manifold X by K, and you can also look at the symplectic reduction of the imploded cross-section by T, and they're the same. So the symplectic reduction of X, the imploded cross-section by T at this point is we can identify with just the symplectic reduction of X at this point. So in some sense we've reduced the non-abelian group action to an abelian group action, but there's an important warning here that we haven't necessarily abelian actions are obviously easier to understand in lots of ways, but we've lost something here in that the imploded cross-section in almost all cases is actually singular and quite nastily singular. So we've, although we've got rid of the non-abelian group action, we've got some nasty singularities to deal with. And in fact, I think it will, the only cases where it's not singular are when the, for non-trivial group actions, I guess, is when the action is essentially SU2 or a product of SU2s. So, so this is the imploded cross-section, the symplectic implosion, and shall I? So if I write here, is that going to be visible? Yes. So one of the nice ways to try and understand the symplectic implosion is via what's called the universal symplectic implosion. So K acts on itself by left and right translation, of course. And hence so there's a symplectic manifold which is naturally associated to K, which is just its cotangent bundle, T star of K. So any cotangent bundle will be symplectic. And this action is Hamiltonian, or both these actions are Hamiltonian. And we can write down the moment maps if we identify the cotangent bundle with just K cross its the dual of its Lie algebra, as we can do, and in an equivariant way, I guess. And then, well, depending on your exact conventions for this identification, you get moment maps. So for one action, just given by projection onto the dual of the Lie algebra, and for the other, you compose that with the coadjoint action of the element of the group. So, and so we can look at why don't I go back here? We can look at the imploded cross-section, the symplectic implosion of this cotangent bundle, and it has very nice property. It's called the universal implosion. So if we take T star K and we take its imploded cross-section, then, so as I say, this is the universal imploded cross-section or implosion. This has lots of nice properties. So one is that it's actually an affine algebraic, complex algebraic variety in a natural way. Which means that, just as for symplectic reduction, we can link up symplectic implosion to some form of geometric invariant theory.
Is this implosion for the K times K action or just one K action?
No, just one of the, yes, sorry, I should have made that clear. So let's say the left action maybe. And then the point is that we have a residual action of K cross T, as I was just going to write down. So we've got an induced action of K cross T. So we started off with K cross K. We took one of those Ks to do the implosion construction. So that K has given us a T action, and then we've still got the other K action. Okay, so we've got an induced action of K cross T, and it has the property that in general, for any x, we have that the imploded cross-section can be identified with the symplectic reduction of x cross the universal imploded cross-section. So I'm using this notation to mean symplectic reduction, and so here we've got a K cross T action, and here we've got a K action. We're taking symplectic reduction via the diagonal K action on these two, and then we'll get left with a residual T action coming from the T action on here. And that gives us the imploded cross-section in general. And so in particular, that tells us that if we started with an X that was actually an algebraic variety, complex algebraic variety with a quasi-projective, say, with the induced Kähler structure, then the imploded cross-section will also be an algebraic variety. So, so this is algebraic if X is algebraic. Well, algebraic meaning shorthand for being a complex quasi-projective variety. Okay, so if we look at an example, the simplest example, so if K is SU2, which we can identify with S3 sitting inside C2, I guess, then we have, if we look at the universal implosion, in this situation, well, for SU2, the imploded cross-section was mu inverse of 0 over SU2 together with the mu inverse of the positive Wahl chamber. And in this case, we just get mu inverse of 0 over SU2 is just a point. And the inverse image under the moment map of the positive Wahl chamber you can identify with just C2 with the origin removed. So that suggests, and it is indeed the case, that the affine algebraic variety that we're looking at here is just C2, with the T action given by multiplication by T inverse, I guess. So that's the universal imploded cross-section, and so that gives us a link with algebraic geometry and geometric invariant theory, as I said. So the link is that we look at the complexification, the complex reductive group, which is the complexification of K, which of course, just as a manifold, we can identify with the coadjoint orbit of the compact group. And if we take B to be the Borel subgroup corresponding to our choice of positive Weyl chamber, so that we've got G is K times B and K intersect B is our compact torus. And if we look at the maximal unipotent, which is, well, I guess can take it as the commutator subgroup of the Borel. So it's just the unipotent radical of the Borel, and it's the maximal unipotent subgroup of G. Then, and so I guess, yeah, we've got the Borel is the complexified torus times this unipotent. And so in general we have just as in the, so if we take G mod the unipotent subgroup, then this is a quasi-affine variety always, such that if we look at its algebra of regular functions, so if we take regular functions on this, so that's just the n invariant regular functions on G, then this is finitely generated. And so that means that this quasi-affine variety has a canonical affine completion, the canonical affine completion, which is which we can think of as being the a non-reductive GIT quotient of the complex group, which is just spec of the invariance. Okay, and so what? Maybe I'll go over here now. So Gilliman, Jeffrey, and Shamar proved that this affine variety, this canonical affine completion of G mod n, has a canonical K invariant Kähler structure such that it's symplectically isomorphic to the universal symplectic implosion. This thing. And so, so the corollary, immediate corollary, is that if X is, let's say, a projective variety, complex projective variety, acted on by G, then the imploded cross-section is isomorphic to, well, X cross the universal thing, which is the universal symplectic implosion, which is just this non-reductive GIT quotient. And then we take the symplectic reduction by K, but we can also think of that as a GIT quotient by the complexified group G. And so we can identify this with the GIT quotient of our original projective variety by the maximal unipotent. So basically we're in a situation where we've got a non-reductive group action on a linear action, I guess I should say, on linearly, with the linear action of this non-reductive group. But in this particular situation where the non-reductive group is the maximal unipotent of a reductive group and the action extends to an action of the full reductive group, then we always get finitely generated invariance, and we can talk about a GIT quotient, and this is what it looks like. So geometrically we've got a description for the non-reductive GIT quotient. So that's sort of why I got interested in symplectic implosion. But so I don't want to go in that direction today. I want to think about how we might have some sort of Hyperkahler analog of symplectic implosion and the sort of structure that it might have. So, so this is the work in progress with Andrew Dancer and Andrew Swan. And so we've already heard about Hyperkahler manifolds this morning, thanks to Tamas, but let me just set up the situation, the Hyperkahler picture just briefly. So I now want X to be a Hyperkahler manifold. So that means, of course, that it's got to have lots of complex structures, well, 3 complex structures, I, J, and K, satisfying the usual quaternionic relations. And it also has to have a Riemannian metric, and such that the metric combined with any of these complex structures gives you a Kahler structure, and so we'll have symplectic forms corresponding to each of the complex structures, and in particular to I, J, and K. And I want to assume that we've got a K action, so a compact group again, on this Hyperkahler manifold, and I want it to preserve the complex structures, and the metric, and therefore it'll preserve the symplectic structures too. And I want to assume that this is a Hamiltonian action in the sense that we've got a Hyperkahler moment map. So a Hyperkahler moment map just, well, mu, which we can think of as mu1, mu2, mu3, going from the Hyperkahler manifold to the dual of the Lie algebra of the group tensored over the reals with R3. So we've really just got the three moment maps for each of these symplectic structures put together to give us our Hyperkahler moment map. And then often I'll want to fix one particular complex structure, I say, and then we can write the Hyperkahler moment map as the real moment map, which is mu1, and then the complex moment map, where the complex moment map is mu2 plus I mu3, going from X to the Lie algebra of K tensored over R with C, and it turns out that this will then be holomorphic with respect to this particular complex structure I. Okay, so then if we've got this situation, we can take a Hyperkahler quotient. We've got an analogue of the symplectic quotient construction, which goes back to Nigel Hitchin and physicists Carl Hader, Lindstrom, Rotchek, I think in the late 80s. And we just do exactly the same thing as in the symplectic quotient case. So HKR Hitchin and Co. Sometimes written with 3 slashes, x 3 slashes k. So this is just the inverse image of 0 under the Hyperkahler moment map, and then quotiented by k. And this gets an induced Hyperkahler structure. And basically it's because if you fix any complex structure, then you can think of this as a GIT quotient with respect to the complexification of k of the inverse image of 0 under this complex moment map, and that gives you an induced complex structure and Kahler structure on this for each of the complex structures that you started with, and they all patch together nicely. Though if you try and take Hyperkahler reduction at some level other than 0, then that doesn't go over so nicely. That's a lot more subtle. But the actual Hyperkahler quotient construction at 0 is very nice.
Excuse me for interrupting.
Sure.
Can I go back to these things on the right? I was a little confused about dimensions. The dimension of the implosion is the same as the dimension of the original space, right?
No. Because you're taking the inverse image of the positive Weil chamber under the moment map. That cuts you down by the dimension of k minus the dimension of t, right? Which is the same as the dimension of n.
So it's not an open set.
No. It's a sort of slice for the n action, essentially. And so, yeah. And it has these nasty singularities. So, when you, as I said, if you try to say, oh, everything's much nicer because I just have to quotient by something abelian, well, you have to worry about these nasty singularities. And 0 is particularly nasty singularity because it's on the boundary.
G moment, not the T moment. That's the inverse image of the Weil chamber in the
Yes.
the algebra of T.
Yes.
Or
Yes,
T star,
yes,
which
yes.
is inside of T star.
Yep. Okay, so in this Hyperkahler picture, so what we want is some sort of analogue of symplectic implosion. So we'd like some Hyperkahler implosion. Maybe HK something like that. And what we'd like it to have is some sort of stratified Hyperkahler structure, and we'd like it to have an induced action of the torus, and we'd like the quotient of this thing by the torus to be the same as the quotient of x, the Hyperkahler quotient of x by k. But I mean, as I was just saying, we'll have, in some sense, maybe gained by reducing the action to a torus action, and particularly in a Hyperkahler situation, torus actions tend to be much better behaved. On the other hand, we're expecting this thing to have nasty singularities, particularly near the inverse image of 0. So we won't necessarily have gained. But so that's what we're looking for. And so since the symplectic case essentially came down to understanding this universal implosion together with the quotient construction, we know how to do the quotient construction. What we wanted to do was to look for a universal Hyperkahler implosion. And I guess I left out something that I meant to say a minute ago. So some examples of Hyperkahler manifolds that are going to be particularly relevant here are that if you take, so here we have the cotangent bundle to K is symplectic, and if you take the cotangent bundle to the complexification of K, then this is actually has a Hyperkahler structure, which is was due to Peter Kronheimer, and also coadjoint orbits bits for the complexified group as well. Kronheimer and Kovalev, I think, and others showed that that these things have Hyperkahler structures. So when we're looking for the universal Hyperkahler implosion, the obvious thing to think of looking for is to take this cotangent bundle of the complexified group and try and find a Hyperkahler implosion of that. So so that's what we're looking for, and what we want it to have is with an induced, so we want it to be stratified Hyperkahler, and we want it to have an induced Hyperkahler action of T cross K, just as we had in the symplectic case. And then what we will do if we've got this thing is define the general Hyperkahler implosion to be the quotient of the product of x with this universal thing, and then we take the Hyperkahler reduction of that by k, and that should give us the general Hyperkahler implosion if we've got this universal one. So what we're looking for is this universal Hyperkahler implosion, and so what we did was first look at a candidate for it in a particular case when K is SUN. So let's first of all recall, so in the symplectic case, what was the universal implosion? What did it look like? Well, we had that the symplectic universal implosion is just K cross K star, but then we have to take the inverse image under the moment map, so that just gives us K cross T star, and then we're quotienting by this equivalence relation, which in this case says that K zeta is equivalent to K dashed zeta dashed, if and only if zeta has got to equal zeta dash, that's the image under the moment map, and then we've got to have, well, K dashed K inverse has got to be in the commutator subgroup of the stabilizer. So in particular, we have that if we take the symplectic implosion and we take its reduction, symplectic reduction at any level zeta in the positive Weil chamber, then by its reduction by the torus, then what we get is the K coadjoint orbit with its natural symplectic structure of zeta. So that's what happens in the symplectic case. And so in the if we go back to the Hyperkahler case, so as I said, we consider the case when K equals SUN. And so then in the mid-1990s, I guess Kobach and Swan and also Nakajima, from different points of view, saw that coadjoint orbits of the complexified group in this case appear in quiver varieties. So here what we're looking at is we want to look at the space of quivers like this, so just linear maps, alphas and betas going between these complex vector spaces, and then we can set up the space of all of these as a Hyperkahler space and take a Hyperkahler quotient. And so if we write M for the direct sum I equals 1 to n minus 1 of quaternions to the power I plus 1, so we can identify that with, if we fix a complex structure, we can identify this with the space of all these maps. So the alphas, I guess, going from Ci to Ci plus 1, plus the betas going from Ci plus 1 back to Ci. And this is Hyperkahler, and it has a Hyperkahler action of the product of these unitary groups, and Kobach and Swan were looking at the looked at just the Hyperkahler quotient of this by the product of the unitary groups. Nakajima had a slightly modified Hyperkahler quotient where you change the natural moment map in the direction of the centre of it. But Kobach and Swan looked at this Hyperkahler quotient where you just take the natural moment map, and showed that this can be identified naturally with the nilpotent cone in the Lie algebra of the complexification of SUN, which is SLN. And this, of course, is the closure of a generic nilpotent coadjoint orbit in here. So this looks, something is closely related to nilpotent coadjoint orbits, and Nakajima's construction was related to other coadjoint orbits. So the idea was that what we should do for our attempt to understand, to guess what hyperkahler implosion should be in the SUN case, should be to take not the hyperkahler quotient by the product of the unitary groups, but by the product of the special unitary groups here. And so this thing is, well, it's certainly hyperkahler. And it also has, so it has a residual action of, well, we've certainly got the SUN acting on the CN that we didn't quotient by here, so that's our K. But we've also got a torus, because for each of the central subgroups in U1 up to UN minus 1, we didn't quotient by that, we only quotiented by the SU. So we'll get a residual action of those, and they can be identified with the maximal torus of SUN. So we've got a hyperkahler manifold with a residual action of K cross T, which is what we want, and well, at least the dimension is correct. So it's just twice the dimension of K plus the dimension of T, which is a multiple of 4 for hyperkahler, and it is what we would expect for the hyperkahler implosion. So that was our candidate for what the hyperkahler, universal hyperkahler implosion should be for the SUN case. And I'm going to have to speed up, I guess. But so we wanted to show that it has a description or descriptions which would work more generally and link up, or analogues of various descriptions in the symplectic case. So so let's go back again to the symplectic case. So for simplicity, Gilliman and Jeffrey and Shamar assume for quite a bit of what they do that K is the product of a torus and a connected, simply connected, semi-simple compact group. And that isn't much loss of generality. It's basically up to some finite subgroups which you can, to either extend by or quotient by, which you can deal with easily enough from the symplectic implosion point of view. But in this situation, then it turns out that the, well, so the monodominant weights in this situation is generated by the fundamental weights. And so what Gilliman and co. did was they looked at the representation of K, which was given by the direct sum for over all the fundamental weights of the irreducible representation, with that as the highest weight. So this is irreducible representation of K with highest weight lambda. And so this is a representation of K, but it's also, you can make it into a representation of T, where T acts on this with weight minus lambda. And they looked at the point in E, which was given by the sum of little v lambdas, so these are highest weight vectors. Just choose some highest weight vectors. And it turns out that you can naturally identify the symplectic implosion with the closure of the KC orbit in E. So they showed, I guess, theorem GJS, which is that this closure is can be identified with the universal implosion, and you can also write it as a disjoint union over all the faces. Sorry, I don't mean is an element of, I mean this is a face of the positive Barr chamber of single orbits, KC orbits, and the stabilizer is the commutator subgroup of the parabolic corresponding to the face. So since I'm running out of time, I won't write this down, but this is just the parabolic associated to the face of the positive Barr chamber. And so that's how you prove what I said before, that, well, I guess it's over here, that the symplectic implosion, you can identify it with the GIT quotient, because you've got one orbit which is just KC mod n, and then the others all have codimension 2, at least 2, so that tells you, and you've got an affine variety. So that tells you that you've got the canonical affine completion. And another thing that sort of comes out of their analysis is that there's another way of describing the symplectic implosion in terms of a certain toric variety, and that's what goes over nicely to the Hyperkahler situation. So it also comes out of their analysis that if you take this closure of the KC orbit, then that's just the K sweep of the closure of the orbit of the same point under the maximal torus, and this thing is the toric variety associated to the positive Barr chamber, or, well, really it's, I think, minus the positive Barr chamber, depending on your conventions. So this cone has an associated toric variety, and we can see that toric variety sitting in the symplectic implosion, and it turns out basically because of the fact that this toric variety is very simple. It's just C to the dimension of T. It's just affine space, but its moment map has a nice section, which essentially means that we can also think of the space that we take to construct the universal symplectic implosion. We can identify this, and we can think of this as being essentially a resolution of singularities of the universal symplectic implosion when we haven't done the collapsing. We can identify this with K cross sub T of this toric variety. Well, I'll just write it as toric. Okay. And that is, I will just take one more moment to write down what the Hyperkahler implosion should look like. So in the Hyperkahler case, for our guess at what the Hyperkahler implosion should be for SUN, which was this quiver variety Q, it can be expressed in the following form, which is a nice analogue of the symplectic situation. So we can write it as K cross T, cross sub T, and then instead of taking the toric variety associated to this, the positive Weil chamber, instead we look at the hypertoric variety. So this is a Hyperkahler thing, which is associated, well, it's supposed to be associated to an arrangement of hyperplanes. So what we use is the arrangement of hyperplanes given by the root spaces in the Lie algebra of the maximal torus. That gives us a nice hypertoric variety. We also have to stick in the Lie algebra of K modulo the Lie algebra of the maximal torus, and then we have to do some collapsing on the boundaries, basically on the boundary strata in this the strata in this hypertoric variety, so that we can also describe it as the disjoint union over the faces, well, the roots really, but again the faces of the positive Weil chamber of, and then the sort of collapsing that you have to do is that this torus gets collapsed further to the stabilizer of the any point on that face, and then the part of the hypertoric variety that we're looking at now is I should have said earlier, I mean, a lot of the symplectic implosion stuff doesn't really go over nicely because although the coadjoint orbit to the complexified group is Hyperkahler, it doesn't have a nice group structure, whereas in the symplectic case, the cotangent bundle on the one hand is symplectic, but also can be identified with the complexification of the group. In the Hyperkahler situation, we don't have a complexification of the non-abelian group. We don't have a quaternionification of the group K, but we do have something that we can think of as the quaternionification of the torus. I mean, you just go from S1 to H star rather than going from S1 to C star, and similarly for a torus. So here we can look at the center of this stabilizer group that we get corresponding to the face, and that's a torus, and we can quaternionify that, and then we have to collapse this by quotienting by the Lie algebra of the stabilizer group rather than just the torus. So that gives us, in the SUN case, a nice picture of the what the Hyperkahler implosion should look like, which then just comes from the group structure, and I've completely overrun out of time, but there are different ways to describe this. I mean, this works for any K, and you can describe the I mean, just as in the symplectic case, the moment map associated to this toric variety, it's not surjective, so we only get the positive Weil chamber here, but it has a section, and that's why we can identify this with this. So in the Hyperkahler case, the corresponding Hyperkahler moment map is surjective, but it doesn't have a section. So we have to, if we don't fix a complex structure, we have to leave the description of the Hyperkahler implosion in this sort of description. But if you fix a complex structure, then the complex moment map for the hypertoric variety is both surjective and has a section, and that's essentially why So then, if you fix a complex structure, you can get back to a situation which looks, a description which looks much more like this, with some extra collapsing on the boundary strata. But anyway, sorry, I've overrun, so I will leave it there.
We have a quick question.
You seem to, I mean, for the hyperkahler quotients, you basically have to stay in the center of the group. You're not taking the quotient at the origin.
I was just quotienting at 0, but you can always shift the moment map by something that's in the center. Yeah.
Center, but now if you're down to the torus, a lot more things become center.
Exactly. Yes. So it should be possible to understand what hyperkahler reduction at a much more general level structure should be by doing it via the symplectic implosion. But what happens, you see, is that so what we don't really understand well enough yet is what the K hyperkahler moment map looks like for this universal thing. So if you fix a complex structure, then it's fine to see what the moment map, the complex moment map is, and to do complex symplectic reductions, which will, in principle, give you hyperkahler reduction. But understanding, so the point is that for the K moment map in the symplectic case, the K moment map on the universal symplectic implosion is surjective. Now, in the hyperkahler case, that's true for the toric picture and the torus picture, but it's not true for the K moment map on this universal thing. And so that's saying that if you wanted to do, that's essentially saying that if you want to do hyperkahler reduction, then there are only some levels. Basically, you can choose any complex value of any value of the complex moment map you like, but then you're very constrained about what the value of the real moment map has to be. And so, yes, so it should fit with sort of pictures of what happens with what's already known about examples of reduction. But yeah, it's a lot more subtle than in the symplectic case.
Okay, so can we then thank Francis again?